Hello everyone, Chris Miller here. Before you watch the video from my class today, I need to talk directly to those of you who are not in my class and watch my instructional videos on YouTube. For those of you who do not know, I'm a professor in the Department of Statistics at the University of Nebraska-Lincoln. Administrators at my university have recommended the elimination of my department. All faculty, including me, will lose their jobs. I will not be able to post an instructional content like this to my YouTube channel anymore. And also, most students in the department will not be able to complete their degree programs here. It may seem strange or odd to you that a university would actually eliminate a Department of Statistics given the growing importance of statistics, data, and data science in general for the world. And we all feel exactly the same here. There is still a chance, though, that administrators will change their recommendation. If you like the content that I make available on YouTube, and if you think that statistics is important, please let my administrators know it. In the content description for this video, I've included information about how to send them a letter or just a small comment. With your help, I hope we can save the Department of Statistics, and if we are successful, I promise to continue posting these instructional videos. Thank you very much.
Let's get started here with class. Today we'll talk a little bit about project number 1 and where I'm at with respect to grading. We'll do a little bit more of cluster analysis, and then we'll also do a test number 2 review. So again, before we get started here, save our stats. In case you didn't see it in yesterday's newspaper, there was an article that I was interviewed for regarding the UNL relied on statistics to choose programs to cut. Statistics faculty say the analysis was done poorly. That's the web-based version of the article. Here's the headline, I guess you could say, from the actual, let's say, PDF of the print copy. UNL statistics faculty slam stats used by university. It's quite a little bit more dramatic there in terms of the phrasing of what was going on there. So if you have access to the Journal-Star, I recommend you read it. This article was in the Omaha World-Herald today as well. The university does have a subscription to the Lincoln Journal-Star, so you should have access to it through the library. And it will give you a little bit more idea of what's going on. So I need to cut off my office hours again early, 2:15 today. The reason being is because I have a graduate council meeting. I am a member of this elected body that oversees the graduate programs here on campus. And one thing that we get to do today is vote on whether or not to eliminate the Department of Statistics' graduate program. So I want to make sure that I'm there and that I can vote. Okay? Some other things, there's so many bad things that you could say in terms of the university's analyses that they've been doing, also the faulty data that they've been using. Here's something that's interesting, just to give you a little bit of a tidbit here. So there are so the university uses what are called metrics to basically say one department's good, one department's bad. Some of their metrics that they're using, you can actually they're actually ratios of two numbers. And based upon what those numbers are, you can actually have 0 over 0. Kind of hard to evaluate a department based upon a 0 over 0 number. And again, this has been made known to the university administration that this is happening. But they stand by their analysis. Obviously we don't have class now next Tuesday because of fall break. Thursday we have a test, so this is actually the last time that we'll have a regular class before an important date that's coming up, and that is October 24th, when the Academic Planning Committee, which is the voice of the faculty, they're the ones that I gave the presentation to last Friday, and they make their own judgment about whether or not to eliminate all these departments. And they should be issuing a public report by October 24th. So you might want to be on the lookout for that. And I guess one last thing to give you the stakes of what's going on here. something maybe you haven't even thought about. This could be the last time that this course is ever taught here at this university if the Department of Statistics is eliminated. Think about that. Okay, do we have any questions before we get started here? Okay, so project number 1. I had hoped to have that all graded before today's class. Unfortunately, it just didn't happen. I'm sorry about that. But I would imagine, I'm hoping by Friday, late Friday, I will have everything graded. I'm a little bit more than halfway through. What you'll notice, similar to like the tests, all my graded comments are basically track changes in Word, or if you're submitted a PDF document, I'll actually put my changes in there as well. Now for the principal component part of the project, basically 2 principal components should be fine. If you notice that the number of eigenvalues that were greater than 1 was just 2. So 2 would have been fine. In my project, I say, well, if you really wanted to, you could do 3 too. In my project answer key, I say that. You could do 3 too. And the main reason why I say that is because it's not that difficult to do 3D plots. And so it allows you to see a little bit more information about the data, but 2 would be fine. For especially number 1, where you have all these plots, or you're looking at these plots and you're making lots and lots of choices, just to help me speed things up, basically what I do is I read like your first few comments about each plot, and as long as I don't find anything wrong, I move on. So I'm sorry, I'm not going to read through everything as I would normally, but that's how I'm approaching this grading to help speed things up. Something I do want to bring up. So your R code and output should be like what you see in my notes, or what you see for like test answer keys in terms of the formatting. Please follow that formatting. You will notice, and maybe I perhaps didn't bring this up before. So in Word here, I'm using a particular style called R10, which is something that's in the project itself. And so that, normally when you copy and paste stuff into Word, let's say that, it's going to look like this. And you can see how some columns are not nicely lined up. I've seen worse than what I just did here, but it's often a mess to read. And so one way that you can make sure that everything's nicely formatted is if you just simply highlight the text that you want, click on R10, boom. You see everything is in a Courier font. The reason why that's important is because every letter has exactly the same width. That will make sure then everything will be lined up based upon the spaces that you see in the output. It will look like your output, generally speaking. Okay? So please strive to do something like that to make things easier for me to see. But even if you're to present a report to someone outside of this class, it's important that everything looks nice too. This is one way to do it. Let's see here. Also, I've encountered this in a few students' projects so far. You need to include all your code, all your output that you're using for a particular problem. Because oftentimes I will copy and paste that into R to verify that you've done something right. Especially if you're doing something that it just doesn't look, maybe you approach it a different way than me. And I want to make sure that you are actually doing it right. Or maybe, let's say you got the wrong answer. I want to verify why that is so I can offer feedback to you about why something didn't work out. If I don't see your R code, if I don't see your R output fully, it's very hard for me to do that. And I have taken off a little bit of points for students who have not done this. Not a whole lot, but just a little bit, just as a kind of a reminder, you do need to do this. This was specifically stated in the project. Let's see here. And then lastly, so there will be times you've probably run into this where you have text let's see here. Let's actually do this instead. Notice how text is just kind of going over where I just, that pairs function there. Text is just kind of going over to the next line of the of what's being displayed. There are worse examples of that. You know, oftentimes I will see, I don't have a, actually I might be able to recreate something. I might see something like this. It's a little bit extreme. But notice how this line is extending over to the next line because it's just so wide. You know, one way to handle that is just to nicely format stuff. But another way to handle that in R is if you, before you get some output, you can change the width of how things are displayed in your R console window. You can do that by saying options width equal, the default is 80 characters, make it something less than 80. Okay? That way, what you're going to copy and paste into your Word document, or however you're doing this, will look a lot nicer. Of course, if you want to, you can use a tool like R Markdown and stuff to do some of this, and everything will be already formatted. It's up to you. Okay, let's talk about cluster analysis now. So we were talking about a hierarchical tree diagram last time, where on the x-axis you have some numbers. This corresponds to the observation number. So we have this this 4 observation data set. And then on the y-axis we have distance, or the measure of similarity that we're using as a way to decide which clusters to join. And so in this particular case, what was joined first was observations 3 and 4 into a cluster. It was joined at a distance of 2.24. Okay, so the way that this is done is lines are drawn up, and then those lines then are connected to say, now we have one cluster. Next, what was done was 1 was joined with the cluster that had 3 and 4. It was done at a distance of 2.44. Again, we have those lines that are drawn up, and then they are joined across. And then the last one is 2.56 for 2 when it's joined with everything else. This is again called a hierarchical tree diagram. This shows you the process that was used to form the clusters. And then as you will see today, it will be helpful for us to then use this to determine where do we stop the clustering process. Because in the end, as you can see here, we basically had one cluster. We want to stop somewhere before that. So let's take a look at the 2 variable data set once again. This was, I think we had 14 observations. Let's actually just take a look at a picture of it again. There we go. So we had 14 observations, and those are some possible clusters just from us looking at it that one could form. And so now let's use one of these agglomerative methods to actually form clusters and then make a decision about where to stop forming the clusters. So as we can see here, the stuff that I had kind of outlined with a dash or dotted red pin there, that's probably as far as we would want to go. We could kind of justify that those observations are similar to one another, but we wouldn't want to go all the way to join everything into one cluster because we see a big separation there in this plot relative to x1. Okay. Okay, so to do the actual clustering in R, there's a function called hclus. Let me turn off my spell check too. And we can then, hclus is going to give us an object that actually has a class of hclus. And then the plot generic function used with this object can then construct the hierarchical tree diagram for us. So here's how it works. First, we need to standardize our data. So we again use the scale function. Our data is in set 1. Again, we have two variables, x1 and x2. We put the results into an object called z. It just kind of makes sense because we're talking about standardized data. Then we find all the distances, pairwise distances between observations. That's what the dis function does. We saw it before. And so for the x argument, that's just where our data is. And then for the method argument, which is the default, Euclidean. So since I'm working with standardized values, this is standardized Euclidean distance. This is the process that we would typically always follow. We put that in an object called dis.mat for distance matrix. And then we use hclust, where for the d argument, we give the distances. And then for the method argument, we give the actual name of the agglomerative method. We are using single linkage here, otherwise known as nearest neighbor. This was the very first of these methods that we looked at before. The results go into clust.nn, cluster nearest neighbor. And I could actually print off what clust.nn gives us, and it is not very useful at all. So clust.nn is a list type of object in R, and we can use the names function with it to see, well, what's actually inside of it. Something that's very important to us is the component called merge. So if I say $merge with clust.nn, what we have here is a history of how the clustering has been being done. So you see minus 13, minus 14 there in the first row. What that means is 13 and 14 are joined together. Whenever you see a minus in front of the number, that is just a way to denote this is an actual observation number. So observations 13 and 14 were joined first. Oh, I should have just simply, let's see. Let's take a look at the plot. There we go. I should just do this instead. So here's the actual standardized values. So again, observations 13 and 14 were joined first. And if we look at, just looking at this on the plot, that should make sense. Those seem to be like the two closest observations. Okay. Now next in the output, you're going to see 1 and 2 were joined. Again, that makes sense. These look to be very, very close observations. In fact, I'll show you very shortly. It just so happens that these are actually the same distance apart as 13 and 14. I don't know exactly how R makes the decision. It's not that important though. You know, it chose to do 13 and 14 first, and then it did 1 and 2. It's not important why. Then we get to the third time that this clustering method is applied. It joins observation 3 with cluster number 2. Notice there's no minus in front of it at all. This is just R's way of saying, oh, I'm talking about what you see in that second row of the clustering history. So if we actually go there, here's our new cluster. What's next? Observations 10 and 12 are formed into a cluster. Okay. Then we'll just do one more of these. Observation 11 and cluster 1, which was the cluster that had 13 and 14 in it. Here's the next cluster. And this just keeps on going and going and going until everything is one cluster. On past tests, I've asked students, actually demonstrate to me on this plot the ordering that everything is done. Give you some perspective of what you might see. Okay. Now, what was the distance that was used when that cluster was formed? That's what the height component of this return list gives us. So when 13 and 14 were joined together, the standardized Euclidean distance was 0.134. For 1 and 2, 0.134. And then next, 1 and 3 were joined. So let's see now. 1 and 2, let's say we're already together, and they were joined with 3. That distance was 0.202. Using the nearest neighbor method's definition of distance between clusters. Okay, yeah. So there's the plot. What I recommend that you actually do, just to make sure that you understand this, actually go through that entire clustering history and keep on drawing those circles, just like I was doing. But do it for the entire clustering process so you have just one cluster in the end. Here's some additional code. So as I mentioned, the class of the object that's returned from hclust happens to be also called hclust. And it was similar to what we've seen before. And note that this line of code in my notes for some reason was omitted. I don't know why. If you say methods class equal hclust, then you see all the corresponding generic functions that are associated with objects of this class. The key one is plot. So if I say plot clust.nn, what R is going to do is look first, what is the class of this object? Then it's going to try to find a function called plot.hclust and implement that. And this is what we get. As I was walking through my notes yesterday, I actually did some writing on it, and I never erased it. Let me do this. There we go. So remember, we had a value of 0.13 when 13 and 14 were joined. Here's 13 and 14. So if I come over here, here's 0.13 on my hierarchical tree diagram. You see something similar for when 1 and 2 were joined. When 1 and 2 were joined with 3, remember we had 0.2. So that's where that corresponds. And if you look at all the heights that were given to us in this object, there's actually a number of other observations at exactly the same height. This is a made-up data set. That's why you see these same exact heights. Okay? That most likely will not happen in practice. But, this plot here, there's probably something that should stand out to you compared to everything else that you see in this plot. And again, we're looking at this plot relative to the distances that were used to join the clusters. Excuse me. What do you think really stands out here?
The big jump at the end to the last.
Exactly. So notice when we join 6, 7, and 8 with the 1, 2, 3, 4, 5. We're at, let's get the actual value. Let's see here. 0.617. And then we see this huge jump to join the last set of clusters, the last two clusters. And we already have seen before, basically that last one is joining those two clusters I just drew on there, is joining those two. And we had just said that, these are quite dissimilar. You shouldn't probably join them together. Look at how that's portrayed then in this plot. We have a huge distance there between when we were at 2 clusters to then when we go to 1 clusters. So what people will do is they will often draw a line, a vertical line like that. And that's referred to as cutting the tree. And what that will signal is this is a place where we can stop the clustering process. Notice how many times the branches of this tree are intersecting this, horizontal line there. It's intersecting it twice. So that means you have 2 clusters. This one and this one in terms of the corresponding observation numbers. So whenever you see one of those large jumps like this, relative to all the distances that you've seen so far, that's a signal to you to stop the clustering process there and go with the corresponding clusters before you would keep on joining. Okay. Are there any other places like that maybe we should stop the clustering process, where the relative distances used to join the next set of clusters is maybe large relative to what we've just been doing? Any other places?
Third one from the left goes up like 6, 7, and 8, going up to 1, 2, 3, 4, 5.
Yeah. So you're saying this versus that.
Yeah.
Okay. Now, this is where you got to be a little bit careful. I'm going to draw a line right here, okay? But I am not looking necessarily at that distance there. I'm not. What I'm doing instead, let me actually erase that. I am looking actually at the distance here to there, because that shows me how much further I need to go in order to continue the whole clustering process. So that's actually what I'm looking at. And I see that that's a big difference. It's a relatively larger distance in comparison to everything else that we've been doing. So that potentially could be a place to stop the clustering process. How many clusters would I have then? I'm sorry, what? 4. Because I intersect here, 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 and here. And so if we look at then our plot, what does that correspond to then? This is a cluster, this is a cluster, and this is a cluster. Oops, sorry. What am I missing here? Because I should have 4 clusters. Let's see, 6, 7, 8. Okay, yeah. Sorry about that. Some of these other methods will actually come up with what I had drawn. So it stops there. Does that make sense? Sure. Is it better than what we had previously when we had this? It's debatable. And that's what you will often find with cluster analysis. More than one set of clusters might be justifiable. You use often graphical tools to help you make that decision about which to go with in the end. And again, there might be more than one justifiable result. But be very, very careful here. A big mistake that students will make sometimes is that they'll focus on that distance rather than the one that I just demonstrated there. Okay? Now you can actually do the cutting of the tree yourself by using in terms of in R itself. You can use the AB line function to do a horizontal line at wherever you want to draw it, let's say at point 4, or let's say maybe 1. And you can draw that line across the plot to help visualize it. You can also, let's see here. Thought I had that demonstrated. You can also, I'm getting ahead of myself. That's okay. There's a function called rect.hclust that stands for rectangle, hierarchical clustering. It is agglomerate method, where you put the results from hclust in there. How many clusters do you want? Let's say 4. What color do you want to draw these rectangles? And look what's given to you. It actually puts everything, it draws rectangles on that hierarchical tree diagram. So you can see it. Okay. Now there is a function called, I would always want to say cut tree, but you notice there's only one T in that function name. I'm going to call it cut tree, where if you say tree for the argument, you put in the results from hclust, and then you say at what height do you want to cut the tree. Then what will be returned to you is the actual groupings of your observations ordered by the actual observations in your data set. So the first, let's see here, the first 8 observations are in what they call cluster 1. The next 6 observations are in cluster 2. If I did this with 4, you can see similar results. Now, why is that important? Well, often what we like to be able to do is, again, have ways to plot our data, like through a scatter plot, maybe scatter plot of the original variables, or a scatter plot of the principal component scores. And then have the plotting point correspond to the actual cluster number, so we can visualize what's going on. And so I can create a data frame that has my data in it. I have then the corresponding cluster results, where if I have 2 or if I have 4 clusters. And what I can do then is do a plot. So here's my plot of my standardized values. So the column 1 is for x1, column 2 is for x2, but they're standardized. I have the plotting character correspond to cluster 4, which again corresponds to when I had 4 clusters. Yes?
So in the cut tree thing, so H, you can either specify the number of clusters or where you want to cut it off.
Yeah,
So
I'm sorry.
H gives you like, where you want to cut off, and it creates how many clusters for you, or you can specify.
Thank you. I did not say that very well. Yeah. So H is the height. K is number of clusters. Thank you very much. So if you remember, in R, there's ways that you can specify colors of plotting points. You could actually give the actual names like red, blue, or whatever. But R will also allow you to use numbers, where 1 corresponds to black, 2 corresponds to something that's reddish, 3 corresponds to something that's greenish, and so on. If you really want to know what the actual colors is, you can do a palette function there. Basically, we have a hexadecimal representation of a color. So plotting character, color as well. So plotting characters corresponds to numbers. The colors can correspond to numbers. And this is what we get in the end. And we can see, indeed, how the 4 clusters are being formed. I suppose you could put a legend there and just say cluster 1 is blue, cluster 2 is red, or whatever like that. You could do that too. We already did that. So what about some of these other clustering methods? Once we go through these, then we'll stop and start talking about the tests. Well, if I want to do the complete method, which would be furthest neighbor, I use exactly the same code, except for I put complete for method. Let's see what we get. Here's my hierarchical tree diagram. Notice where I've cut the tree. I cut the tree at a height of 2, which corresponds to something similar to what we saw before, where I had just 2 clusters. But notice, now I have a different location for that other one. Based upon what I see, and again, I'm looking at now the distance between here and here. That's what I'm visualizing to decide, should I cut the tree or not? Again, I'm looking at distances that seem to be are large relative to what I've already been doing in the previous history of the clustering process. And I can see that indeed that seems much larger than what we had. So I decided to cut the tree there, and that will give us 3 clusters. Notice that means 1 through 5 are together, 7, 6, 8 are together, and then 9 through 14 are together. Let's see here. Yeah, sorry, I'm going a little bit too fast, trying to get through all this. Let's say I use the average method. Remember what the average method does is finds all distances between points in different clusters and then averages them. Okay? And here's the hierarchical tree diagram, and we get something similar to what we had for furthest neighbor, or the complete linkage method. Potentially here as well, potentially. Something you want to be careful about is that you don't want to have too many clusters. Because if you have too many clusters, then it becomes harder to interpret. Your clusters become very, very small in terms of number of observations. In my program, I show how to do the centroid method. As you might expect, there's a method equals centroid. I don't know why R is set up like this, but there's a computational quirk. That's the only way I can describe it, where when you put in the distances in H+, you need to actually have the distances squared. So whatever let's say your dist.mat is, like what I had, just do this. I've never been able to figure out why exactly. Okay. Let's see here. So there's other ways to do cluster analysis in terms of R. There's an Agnes function. You're welcome to look at it, but we're not going to use it here. And I think this then is a good place to stop so that we can start talking about the exam. Any questions? Okay. Let's see here. So what material? Graphics, principal component analysis, cluster analysis up to page 25 of the notes. So nothing that we did today. Okay? But the cluster analysis stuff that we did last time is fair game for me to ask questions about. So what that means is can I ask you a question about how to use the H+ function? Okay? I think that's just fair, since we're just doing it right now. But I could ask you questions about, describe to me the furthest neighbor method. I could have you actually walk through a by hand example with it too. The format of the test, same as before. Closed book, closed notes, closed video. What you can use is any of my R programs. You can use the formulas function PDF. You can use the R help. That's in R itself. You'll be using the tests. You'll be using the computers here in the classroom to take the tests. I will make the tests available at 12:25 to give you a little bit extra time. You don't have to start earlier, but it will make it available then. I do write the test so that you should be able to complete it in 1 hour and 15 minutes. Let's see here. So again, there will be a Word file that you'll be able to download from my website. Put all answers in that Word file. You can use text-based expressions for symbols like MUHAT for MUHAT or something like that. You need to turn in the tests by 2 p.m. I just recently put something up on Canvas for a place for you to hand it in, similar to what you had for test number 1. So just upload it. I think it went pretty well last time. You don't need to check with me that indeed that you turned it in. Just remember to hit submit at the end so that it is actually submitted the test. Also, make sure to save a copy of your tests. So you can email it to yourself, for example. That would be a quick way to do it. We do know that computer problems can happen. And if the worst thing does happen, I will let you use a laptop. So bring your laptop if you don't normally bring a laptop, and you can use that if we're having lots of computer difficulty. I think an issue that sometimes students have in completing my tests is with respect to speed. So if a problem is taking you 30 minutes to figure out how to use PrinComp to do a principal component analysis, that tells me you haven't studied enough. So while I don't want you to have to memorize code coming into this class, you should have enough familiarity with it that, if I ask you to tell me how many principal components should be used for a particular data set, you'd be thinking, oh yeah, that's PrinComp. What again is that syntax though? Let me go find it in one of the old programs, copy paste it in my program, change the data set name, change the variable names, and then you're set to go. But if it takes you 10, 20 minutes to figure out where is that code, I don't remember what function to use, then you haven't studied enough. Any questions? So in terms of the structure, remember to show your work. When computations are needed, all our code and output needs to be included in your answer. I will not give you full credit. One reason why I want you to do that is so that I can figure out what you did wrong if something does go wrong. And then I can give you partial credit. The problem types are same as what you saw in the previous tests. Oftentimes I will give you a data set and say, okay, go do some computations and then go do some interpretations. Typically that's how these problems are structured. There will be one short answer problem set at the end of the test where the parts are not connected in any way. In terms of the actual test number 2, this is what's on it. This is the current version. It could change a little bit, but I'm not anticipating it will change much. Problem number 1 is a graphics. It's a problem from the graphics section. I give you a data set. I ask you to construct a plot and then interpret it. Then I have another part where I ask you to construct a different plot, interpret it. Okay? Similar to what you had for project number 1. Problem number 2 on the test. Here's a data set. Let's do some principal component analysis on it. The first part, should we use a correlation or a covariance matrix? Why? Second part, how many principal components should we use? Then there's like a third, fourth, maybe a fifth part. I don't remember off the top of my head. Where I'm going to have you do some stuff with the principal components, such as maybe interpret them, such as maybe do something with the principal component scores. Maybe I have you do a plot of the principal component scores and interpret it. Maybe I actually have you write out the actual equation that's used to find the principal component score for, let's say, the first observation, the first principal component, similar to what you had on the project. I might have you actually write out in formal notational form a principal component. Those are the types of things to expect there. Then problem number 3 is a cluster analysis question. Right now, it is worth 20 points. And I ask a general question about, agglomerative methods. So, we've talked about 4 different agglomerative methods. So, study up on what those methods are. How would you actually implement them? If, let's say, maybe you were doing them by hand. And then problem number 5 is a group of short answer questions. So that's what the test looks like. I don't anticipate it should be difficult. But then again, I'm not the one who's taking it. I don't think that there should be any surprises. Yeah. Any questions?
Can you explain briefly if there's is there ever a time where the covariance matrix is better than the correlation matrix for PCA? Because it always seems like the correlation matrix is just better always, and the covariance matrix is just some sub thing that you can use, but it's not better.
Well, the goblet data set. Potentially, that would have been the preferred way to do it. Yeah. I think both would be justifiable. So that is one example. The key is you need to have your data in the same units, and maybe there's a particular variable where you're okay with it, let's say, being more dominant than another variable. And you can imagine, let's say, if you're measuring, lengths of various things, it doesn't have to be goblets. Maybe it might make sense to let one variable be more important than another variable. Okay? But generally speaking, the correlation matrix would always be used. Any other questions? Yes.
For that example with the coded data, when you said that potentially the covariance matrix could be a better option,
yeah.
Do we always have to consider to standardize our data? Because I recall in that data set we kind of divided the variables by X3, I think was measured in 3, something like that.
So in that, with that data problem, the researchers they wanted, if a goblet, let's say, was this big, it had a certain shape, and another goblet was this big and had basically the same shape, they wanted those to be grouped together. And so what they thought one way to handle that would be to actually divide by that one variable, I think, which was the overall height. So is that actually standardizing, where we take the mean divided by the standard deviation? No. But it is, in a non-statistical way, standardizing. How about that? Okay? And so, that potentially then, if you're doing that, that can potentially, in some respect, take the role of a formal standardization. It depends upon the archaeologists, what they would want to do. Other questions? Okay, so let's do a little bit of a review here. So, graphics. How to implement, how to interpret for all these various plots. That's the big picture. What we're trying to do in this section, as in a purpose, is to show as many variables as possible on one plot on exactly the same time. This is a multivariate data analysis course, so we want to be able to graph multivariate data. Some of these plots are ones that you've kind of seen before, or little modifications of them. Other plots are different. So one that you probably saw before was a side-by-side scatter plot. We looked at two-dimensional scatter plots where we tried to add, let's say, additional dimensions, additional variables to the plot by working with the plotting character, the color, the type, the size. Speaking of size, that's where the bubble plot comes in. Now, remember, whenever you do a bubble plot, you can't work with a negative value for this third variable that's the size of the bubble. So you have to make an adjustment for it. I could ask you a question about that adjustment that's made. Why does it work? Why does it make sure everything is always greater than or equal to 0? That hopefully would be a simple question. This reminds me of something that I saw, I think at least one group, maybe two groups so far, do on the project. They decided to use absolute value rather than that other adjustment to make sure everything was greater than 0. I know I briefly talked about absolute value in class, but I thought at that time I also talked about what are the side effects of it. So for example, let's say if I have, two observations where one observation has, let's say, an x3 of 2, another observation has an x3 of negative 2. How would they actually be represented on the same plot? By exactly the same size circle if you take the absolute value of x3. In most cases, you wouldn't want that. Because it's two variables with completely different values, but they're represented exactly the same way in the plot. We also talked about 3D scatter plot as well. Then we got into some other plots that probably most of you hadn't seen before you got into this class. A stars plot. A question that I've asked before on tests is, tell me how multiple variables are actually displayed on a stars plot. Well, you have each ray represents a variable, where how far the ray goes out corresponds to the size of that variable value. What's a downside of using stars plots? Well, you have to have a star for every single observation. So if you have lots of observations, is this plot, if you have lots and lots of observations, is this plot something that you want to use? Probably not. But as long as you don't have too many, that they're manageable, then this can be a very useful plot. Especially if you have some way maybe that you know of beforehand where you can organize everything. So for example, with the project, we were able to organize it by the position. And you could see how those offensive linemen just stick out compared to all the other positions. Now, something that's more general is a parallel coordinates plot. You could potentially go with a lot more observations with this. This is probably my favorite plot out there. One potential problem that you can have if you have lots of observations is, you have a line for every observation. Those lines might be on top of other lines. And so that's one thing that you have to watch out for. There's ways around that was discussed as well. But there's not a perfect solution. And then there's a trellis plot. How are we actually representing multiple variables? Well, it's often that conditioning part. And you don't have to have categorical variables that you're conditioning on. You can use what's called a shingle to condition on particular values of a continuous variable or a range of a continuous variable. Okay, so that's the graphics section. Now the principal component analysis section. What's the overall purpose of it? Well, we have lots of variables. We would like to be able to see if we can reduce the dimension that we view the data by looking at a smaller set of new variables called principal components. How does it work? Well, that's where this eigenvalue and the eigenvectors come into play relative to the covariance matrix or correlation matrix. How would you actually write out a principal component in a formal manner? Well, why is the correlation matrix typically used? We talked about that already. How would you choose the number of principal components? I know we talked about a discrete plot in class. That's my last choice of how to choose the number of principal components. Look at the number of principal components that are have an eigenvalue that's greater than 1. That's a good way to do it. What I tend to use first, though, is I want to get a certain percentage of the variability in the data explained. And so I often look at that cumulative proportion of variability that's explained. Make sure you understand why I'm saying variability there. You know, what's the variance of a principal component? The corresponding eigenvalue. Yes?
In the project answers, I think one of the things you wrote was having a cumulative variability greater than 0.8. Is that like a standard?
There isn't one standard. That's often what I attempt to do. Doesn't mean I always would do it. And in the project answer key, I think two principal components was 70-some%. I think 77%. So, you know, just think of it from an intuitive point of view. We're trying to account for as much information in the data that's as possible. How do we quantify information? Variability in statistics. And so if someone told you, yeah, you have 80% of the information that you need to know about the data, typically you might say, okay, I can live with that. So that's where that comes from. But it's not a hard rule. You know, you should think of it from the other point of view of, well, let's say I have 2 principal components only give me 30% of the information. I bet you're missing out a lot. Next, how do you find a principal component score for a new observation? In terms of how would you do it with our code? How could you do it, let's say, with by hand calculations? Could you write it out? How do you interpret your principal components? I wasn't seeing this. My answer key, if you notice for the project, really focuses a lot more on I have this variable, this variable, this variable. It's contrasted with this variable, and this variable. What I was seeing a lot of students do in the project, which was fine, but maybe a little bit harder to do, saying it was like a measurement of strength versus explosiveness. Maybe it was yours, but it wasn't only yours. Others were doing it. It's fine to do that, but you know, just obviously be a little bit careful. You know, a surefire way to get the right answer is if you, let's say, first focus on the variables and say it's contrast between these and these, and then if you want to expand upon that and say, looks like that's strength versus explosiveness or something like that. Now, I didn't take off points if you only did the strength versus explosiveness, as long as you got it right. But I'm just saying that just from a general standpoint of helping you make sure you get the correct answer. Start with particular variables and then go to the more general interpretation. We looked at a number of different ways to plot principal component scores, and then how to use PrintComp. Lastly, cluster analysis. Again, up to page 25 of the notes. So you need to know the basics of how to do those 4 main agglomerative methods. You know, could you do it by hand, for example? You know, how, you know, what's really the thing that makes these methods different? It's how they measure the distance between the different clusters. Make sure you absolutely understand that. We did a very basic hierarchical tree diagram too. I think it was like actually page 25. Make sure you could do that. Why do we standardize? typically? Well, again, you don't want one variable. We're measuring the distance between all these variables and stuff, and so you don't want, let's say, one variable to distract from the other variables. The big picture for clustering methods, mainly, we're just focusing on this right now. I think that would be fine. Here are the 4 different methods that we focused on, and I think actually I just said all that. Also, the good versus bad clusters. Okay. So that's all I had in terms of the test review. Do you all have any questions about the tests or any of the material? I think in the end, in terms of, at least when I've been using this format of tests and this corresponding course over the last few years, this is probably the least amount of material that I've had, because normally we would actually do factor analysis completely, and then maybe even a little bit of cluster analysis for test number 2. So I guess that might be helpful for you, because there's less material for you to study.
Does a stars plot also not handle negatives very well?
It works out fine, because basically what is very similar to how parallel coordinate plot would handle a negative. It finds, let's say you have a variable called x1. It finds the smallest value, let's say it's -5. And essentially for that variable, -5 represents the very center of the star for that variable alone. And then let's say you have an observation that has a value of -3. Well, then it's going to go out 2 units. Let's say the largest value for that variable is 10. And so if you have that, then that 10 is going to go out as far as possible on that plot. And so everything is relative to the minimum and to the maximum, just like the vertical axis on a parallel coordinates plot. Good question. Other questions? Well, I don't want to keep on going in the cluster analysis notes today, so we have like 10 minutes of more material I could do. So let's end it with this. What's next in our class? I'll have office hours. Need to end at 2:15. There's no class on Tuesday because of fall break. Thursday, next Thursday, I will make the tests available starting at 12:25. So if you can get here early, you can have 5 extra minutes. If you can't, that's okay. I'm not making the test any longer. I don't know if maybe I didn't. Did I say when the test is going to end? 2. Okay, yeah. So you have until 2 if you would like that long. I don't make the test longer though, even if I'm giving you that extra time. Looking further ahead, hopefully the following Tuesday after our test, I'll have project number 2 ready for you. Also, looking even way further ahead, test number 3 is Thursday, December 4th. So, any questions? Okay, that's all for today.